Now it is live stream.
Yeah, now it is live. Now it is live.
Okay, can you make me as host ACARR, ACCAR? ACCAR, CUSAT as, yeah, thanks. Now I am host. Okay.
Now it is YouTube. YouTube is live and program is in your hand. So we can continue.
Yeah. So, welcome to the South Asian Meteorological Association online lecture series on radar meteorology, with a special focus on principle and applications of Doppler weather radar in weather forecasting and research. So today, the third lecture will be handled by none other than our chairman of the advisory panel, Dr. Pradhan sir. He has already covered his first lecture on the basic fundamentals of radar and its principle. So today he will be talking on radar principle, including scattering mechanisms, various type of scattering mechanism pertain to each wavelength regions of radar. Before beginning, I invite AVM retired Professor Tyagi Saab to propose the presidential address. Tyagida.
Thank you, Abhilash, and once again, let me compliment your team for organizing this and the support provided by entire Sama team, how to put this on live streaming from different locations. People could coordinate and make it live streaming on the YouTube. So it is a great teamwork, and I am happy that this lecture series is evoked a great response from both online and also offline on the YouTube channels. So this is a matter of great satisfaction. And again, Dr. Pradhan being the chairman of the advisory committee and also delivering today's second lecture, he also needs to be complimented. We are really thankful for planning this program with the support from all institutions, key persons there, and CUSAT hosting this. So this is the lecture, which was the radar series lecture was overdue. I think in the country there is no such training program which puts it across to the large spectrum of users, researchers, students. So that way this online lecture series is of great value, and I'm sure has brought out the lecture series and the subsequent lectures. If you go through the program, each one has got specialization. So with the foundations in the first two lectures, thereafter Dr. Kannan and Gajendra Kumar will take on the lectures. Again, fifth lecture is by Dr. Pradhan Sahab. So he'll bring the real lifetime situations in which we monitor thunderstorms by radar and how it is useful in warnings. And so that way, both from theory to the products and its application in research and the forecasting will be covered. So my appeal and request to all participants is that please take it seriously. It will immensely benefit you both in your profession and also as a amateur weather enthusiast. There are many people who may not be having a degree of meteorology, but they are interested to know about the weather. So these programs are also meant for them. We want to include a wider community in the weather awareness through these outreach and training programs. So with these opening remarks, and I welcome and thank Dr. Pradhan for delivering this lecture on the scattering and radar types of radars, so particularly the radar equation part of it. So once again, my appeal to the participants, make full use of it. I know the last lecture also evoked a good number of question answer sessions. So please feel free to ask questions in the QA session. Thank you.
Thank you very much, sir. With your permission, should I start my lecture, sir?
Yes, I'm. Please.
Dr. Abhilash?
Yes, sir. It is visible, sir. Visible.
Oh, okay. Oh. Good afternoon, as per the Indian Standard Time, to everyone who is present in this lecture series on radar meteorology and the training which is organized by SAMA. So in my first lecture, I gave you the introduction, brief introduction and very basic. I know that this information was too basic and too simple, but it was necessary that everyone should know that what was the background of the radar meteorology and how it has become so popular and advanced in the recent years. So after the introduction of different kinds of the radars, non-Doppler, Doppler, and some basic terminologies and the things which I have discussed in the last lecture, I'll wait for the questions at the last, after the completion of my second lecture. So let's join once again here that what is basically the Doppler weather radar. So in brief, I can say it is a state-of-the-art weather radar which provides so many things. What are the things which may get many things, because it is one of the most versatile tools for monitoring and predicting the system in the nowcasting mode. As we all know, the meaning of the nowcasting is to have the prediction for a small duration, say around 3 to 6 hours. But this duration is sometimes becomes very important and crucial when we are going to see a very highly accurate prediction with the help of Doppler weather radar. So rainfall rate, total rainfall associated to a cloud, intensity of the cyclone, speed of the winds, direction and movement of the system, direction and speed of movement of thunderstorms, tornadoes and cyclones, estimation of the wind speed accompanied with the cyclone as well as a thunderstorm. It means it is so dynamic and versatile that it can provide almost everything with respect to any kind of the atmospheric system, whether it is a thunderstorm, hailstorm, tornado, cyclone, heavy rainfall, or maybe anything related with the hydrometeors and the atmospheric science. So for the 3 hours duration here, 3 to 6 hours duration here, the Doppler radar plays an important role because it not only provides the information about the precipitation contents, it provides the direction of movement of the system, in which direction the system is expected to go. So all the things we will discuss one by one in the subsequent lectures here, and then we will see that how much information we are getting from Doppler weather radar. And I'm showing here, it is able to provide the vertical extent and the three-dimensional structure of the clouds. Usually, whenever we are looking for any image of the cloud, it is two-dimensional. But if you want to make its cross-sectional, vertical cross-section, horizontal cross-section in the 3 dimensions, so we can find out that what is the horizontal extent, what is the vertical extent, and what is the depth of the cloud. Many things can be understood from the Doppler radar. And as I discussed in the last lecture, the meaning of the Doppler, because the Doppler principle is applied to the electromagnetic waves, and Doppler means relative velocity. Relative velocity means when radar is stationary and the clouds are continuously moving, winds are moving, the system is moving, so we are able to apply the Doppler this thing effect on those phenomena. So With the help of the Doppler principle and the Doppler radar, we are able to get many information, what is shown here in this slide. Damage potential of the severe weather phenomena, winds associated with the cyclone. What is the meaning of the damage potential? Suppose there is a simple thunderstorm, which is either a single cell or a multiple cell, or there is a squall line kind of the system, which is a chain of the so many thunderstorms joining the each other. So it is able to produce the winds of the order of around 80 kilometers per hour, 90 kilometers per hour, and gusting to around 100 kilometers per hour. So in this case, what will be the damage potential that we can find out from the Doppler radar, that at what is speed the system is moving and how much wind it can create. So precise prediction of the movement of the thunderstorm in which direction it's going, and where this thunderstorm prediction is important the most. In the case of the aviation, in the case of the defense, in the case of so many other phenomena where short-term prediction is very important. If you talk about this launch of the missile or the testing of the missiles here, the Doppler radar plays an important role, and therefore at every place, wherever the defense locations are there, or anywhere in the world, or anything which is to be precise with the wind speed and wind direction, the Doppler radar has no comparison as such, because it is the only tool that can give us information in the next 2 to 3 hours what is going to happen. If there is any thunderstorm which is associated with the lightning, you know that lightning and thunderstorm with heavy rainfall and the wind speed is dangerous to the rocket launching or the missile launching or whatever is the case here. So for the space technology, for the defense, for the weather forecasting, for the hailstorm, for the transportation, for everything, the Doppler radar plays an important role, because it is giving the information for the next 3 to 6 hours. Quantitative rainfall, that how much rainfall is expected in the 2 to 3 hours. Estimation of the gusty winds associated with the thunderstorm. Detection of the hailstorms, tornadoes, etc. And from these 2-3 slides, you can understand and see that how dynamic and useful is the Doppler weather radar. But there are certain limitations of the radar. What are the limitations? One, the first limitation I have already discussed, that it's able to see only few hundred kilometers, only say around S band, that is able to see 400 to 500 kilometers, C band 250 to 300 kilometers, X band only up to 100 to 150 kilometers distance. So this is the basic limitation of the radar with respect to the different bands and the frequencies. So that was the first one, that because of the curvature of the earth, you are unable to see beyond a certain range. Another is that Doppler radar is a sophisticated kind of the system here, and the interpretation of the echoes require this kind of the training which we are providing to you. You can see in the website of any country wherever the Doppler radars are there. For example, I'm talking of this India Met Department. So you can see the website, you can see the Doppler radar, but if you want to interpret those things here, that what is there in the PPI, MAC-Z, PPI velocity, VVP2, and many other images are there, you cannot directly say that what information you are going to derive from those images. You should know the understanding of the images, that what's the meaning of the different color, this thing table there, what is the relation between this Z, that is a Z reflectivity, and rainfall rate, and so on. So this requires your training, and that's why this Sama has taken this challenging job for everyone who wants to be expert in the analysis of the image, Doppler images, and not only the analysis, to implement it for the prediction here. And here we all will be discussing many things here, and in my I got some more lectures to discuss where I'll show you the actual this thing here, the particular thunderstorm sequences coming here, and then we will make a movie loop of everything, all the thunderstorm there, and then we will have a discussion. Okay, the thunderstorm has been developed here. Now, in which direction it is going to be expected here, where it will go. So we should know the direction and speed of movement of a thunderstorm. And remember, all thunderstorms do not move with the same speed. If it is a single cell thunderstorm, it will move with a lesser speed. Multiple cell, because it is having a lot of energy there, it will move with a much faster speed. And if there is a squall line kind of the structure, if it is a straight kind of this structure or it is a curved here, there will be a difference in the speed. So you cannot say in general that a particular thunderstorm moves with a speed of 40 kilometers or 50 kilometers per hour. You have to see the structure of that particular one. And for that, I have already prepared my 2-3 presentations where I'll show you that how the sequence of thunderstorms, clouds are going there, and with what velocity they are going to achieve here, and at what time they will reach to a particular place. So these things we will discuss here subsequently one by one. Another limitation is that due to beam widening and the increasing height above the earth with increasing range, meteorological targets smaller than the resolution volume cannot be studied. Whenever the signal is going from the antenna that I have shown you in the last lecture, there is a beam widening here, which is in the form of the pencil beam when it is coming out of the radar, but when it is going away and away, the beam widening takes place here. So if the target is much smaller, I'm talking of the whole volume, if the target is much smaller, the resolution becomes very poor and we are able to see it, but its analysis will be slightly poor. So these are some of the limitations, but if we compare the applications, utilization, the versatility, the dynamicity of the Doppler weather radar, on the other hand, the limitations are can be ignored or can be neglected therein as compared to the information received from the Doppler radar. Here, one slide I have put here, and you can see that how beautifully the different cyclones have been monitored by the Doppler radar. The first one on the left top here is the Cedar cyclone, which was there in the Bay of Bengal on 15 November 2007. Phylline cyclone on 12 October. Phylline cyclone, which you can see in the middle. The Doppler radar S-band, which is located at the Visakhapatnam of the east coast of India, that beautifully tracked the overall path of the cyclone. And as per the prediction of the IMD, the Doppler radar confirmed that it was having the intensity of almost a super cyclone. That Phylline cyclone was nearing super cyclone when the wind speed was around 200 kilometers per hour, and that was authenticated by the Doppler radar at Visakhapatnam that the wind speed was very high. Another cyclone which you are looking on the top right hand, Hudud cyclone, exactly on the same date but 1 year later, 12th October 2014, and 3 more cyclones I put here, so you can see how beautiful images are picked up by the Doppler weather radar. Beautiful eye, the eyeball region of the cyclone, and how much intensity of precipitation, how much wind speed is associated, and a beautiful structure can be seen from Doppler weather radar, which you can see from these images. So subsequently, when the training goes on day by day, we will be able to see so many things with respect to the outcome of the Doppler weather radar. Now question comes, when we are finding the reflectivity, so how it is converted into the rainfall and the intensity of precipitation. So this relation which converts the reflectivity or the radar reflectivity factor Z or Z into the rainfall rate R, the relation, this empirical relation is given by Z is equal to A R to the power B, where A and B are empirical constants. If we take what Marshall Palmer has suggested, that in general, the value of A, constant A, can be taken as 200 and B as 1.6. This relation is named after them, Marshall and Palmer. So what they suggested, that when we are taking this 200 and 1.6, then most of the kinds of the rainfalls may be estimated from this. But remember, this ZR relation, it is a variable relation. I'm talking of the variables A and B. These are not constant everywhere because the values of A and B change from place to place, season to season, rain to rain, and from one country to the another country. What are the values of A and B in New Delhi? These may not be satisfying in the southern part of the India or eastern part of the western part, or it may not be applicable in the neighboring countries or any other European countries or even the southeastern countries. So we have to find out the values of A and B with respect to the different seasons and with respect to the different rainfalls. So in that case, this relation plays an important role, that how the reflectivity is converted into rainfall rate. So the rest is a simple mathematics. I have taken the logarithmic scale, taken the logarithmic log here z multiplied by the 10, and then this 10 log to the base 10 r. This is basically giving us the value of the r, and then we are taking the exponential of the r, that is a anti-log, then we are able to get the rainfall rate. So when we put it in a simple program, computer program, and when we put the value of the z, it is automatically giving us the value of the rainfall rate. So with respect to this z, the rainfall rate is this. With respect to this z, but one more thing I would like to say here is this relation z is equal to a or b is very much useful wherever there is a single polarization system, or even if it is the dual pole system is there. But in the dual pole system, when we are having the two kinds of the polarization, horizontal and vertical polarizations, in that case, although it is embedded there in the software, but it may not be required because some other parameters are there in the dual pole system. For example, this correlation coefficient, differential reflectivity, phi, dp, and some others are there, which you will see later on. So with the help of that, we may not be requiring that value of the r here, but wherever the single polarization system is there, this relation is very, very important, and we can convert the value of the z into rainfall rate. So I'm coming back to the today's topic here. I'll discuss about the scattering, two kinds of the scattering, Rayleigh and Mie, radar range equation for point and distributed target. So I'll confine myself to the distributed target, description and significance of the parameters in the radar equation, and some definitions related to the radar. Now, why I'm going to the very basic of this radar meteorology that you should understand. I may go to the advanced applications and so many other things, but the question is, unless we understand the phenomena of the scattering, what are the characteristics of the Rayleigh scattering, why we are using the Rayleigh scattering, why we are not using the Mie scattering, when where Rayleigh is used, where Mie is used, what is the radar range equation, all these things are supposed to be known to a radar meteorologist. So if you are working on a radar system, or if you are analyzing it, or you want to become a good radar meteorologist, you should know each and everything here. And that's the reason I have taken everything in my discussion here, that how we can understand the simple things. So let's start. Scattering is the phenomena in which the electromagnetic waves or the light waves, whatever is there, they are going in the different directions. So we are not using the word the reflected echoes. No, reflection is only in one direction, but scattering in all the directions. So when the signal is going to the target, I'm talking of the radar signal from the hydrometeor, in our case, they are scattered in all the directions, and only a small part is coming back to the direction of the antenna. So scattering is the phenomena in which the electromagnetic waves are going in all directions with the scatterer, which is the target. Now, what is Rayleigh scattering? Let's understand in this slide. When we apply it, when the size of the target is small compared to the wavelength of the radar, the backscattered energy is inversely proportional to the fourth power of the wavelength. This is termed as Rayleigh scattering. So now this particular definition gives very important informations like this. Number one, if the size of the target is small compared to the wavelength of the radar, then where Rayleigh scattering is applied. When the backscattered energy, what is backscattered energy? The energy which is coming from the target, coming back in the direction of the radar, it is called backscattered energy. It is inversely proportional to the fourth power of the wavelength, 1 upon lambda to the power 4. It means wavelength is large, the backscattered energy which is coming back to the radar is less, very, very less. It is the inversely proportional to the fourth power of the wavelength. Larger the wavelength, smaller is the energy which is coming back to the system. This is known as Rayleigh scattering, and this definition we will apply in the mathematical discussion of this Rayleigh scattering. The backscattering cross-sectional area is directly proportional to the sixth power of the diameter of the backscatter. So this is another thing. One thing, that is the backscattered energy is 1 upon lambda to the power 4. But on the other hand, the backscattering cross-sectional area, the area cross-sectional area which is able to provide the backscattered energy, it is directly proportional to the sixth power of the diameter. It means larger the drops, its sixth power is responsible for the cross-sectional area, and accordingly the energy which is coming back to the receiver is calculated. So this phenomena is applied in the hydrology, that is in the meteorology or the radar meteorology, because water drops are having the diameter of the order of 5 millimeters, 10 millimeters, say up to 500 millimeters, or even 50 millimeters and up to, not 50 millimeters, 5 millimeters and up to 10 millimeters, say 1 centimeter. After 1 centimeter, even if it is 1.5 centimeter diameter, the size does not remain spherical, it becomes slightly ovoid. And in this case, because of the this thing, coalition of so many, what should I say, the drops, they form a bigger, larger drop, and it does not remain spherical. And sometimes the water drop becomes a snow or in the form of the hail. So Rayleigh scattering is applicable. Now, if you are using the different bands, X band 3 centimeter, C band 5 centimeter wavelength, and S band 10 centimeter wavelength. So S band 10 centimeter, C band 5 centimeter, X band 3 centimeter. These are large enough as compared to the diameter of the drops, because diameters of the drop is usually 1 centimeter diameter, 1.5 centimeter diameter. So Rayleigh scattering is applicable in the case of the weather radars, and especially with the Doppler weather radar, where we can apply. Here we are going to see a parameter K, which is K. We can see here the formula, and in this the K is a parameter related to the complex index of refraction of the substance, and is given by capital K is equal to m square minus 1 upon m square plus 2. And this K is basically the complex index of refraction. Small m, K is related based on m, and K is known as the parameter which is based on the complex index of refraction, and small m is equal to n minus ik, where n is basically the refractive index of the medium and K is a complex index of refraction. That we will discuss later on. Yes, please. Somebody is raising the hand if there is any question.
Sir, we can take the questions at the end of the session, sir.
Sure, sure. Okay, yeah. So this diagram gives the idea of the scattering as well as the Rayleigh scattering. And you can see here the incoming wave is coming there, and then, and in that case, when the incoming wave is there is a scattering, and the size of the target is smaller than the wavelength. So this Rayleigh scattering is applicable. Another diagram which I have put here is that this is either from the air molecules or from the water molecules. It is applicable in both the cases. So that is the intensity of the signal which is coming back is inversely proportional to the lambda to the power. Just excuse me. Can we remove this? Okay, no problems. I can move. Thank you. So this is the case of the Rayleigh scattering. And now we are coming to the Mie scattering. When the size of the target is large, comparable to the wavelength of the radar, the scattering is termed as Mie scattering or Mie scattering. So you can see here, when the size of the target is much, much bigger than that of the incident wavelength of the waves, electromagnetic waves, then we are calling it as a Mie scattering. In the case of the meteorology, our hydrometeors, which are containing the water particles, these are smaller as compared to the size of the, that is a wavelength of the radar, that is the reason. So we are not using the Mie scattering, we prefer the Rayleigh scattering, and accordingly we discuss. Now, few definitions of the radar parameters I'm putting here for the information, because whenever we will discuss anything about the radar equation and its applications, then these things will be applicable. The first definition is the pulse width. I hope you remember when I was discussing about the pulse radar, that time I have shown you this diagram. In this diagram, we can see that there is a pulse which is going high, and when the pulse is high, the transmission takes place. When the pulse is low, the reception takes place, the receiver is connected. So whatever the width of this pulse is there, that is, you can understand from this pulse that if the width is more, then the time of transmission is more. So the duration, the transmission time of the pulse, usually measured in microseconds, is known as the pulse width. It is also called the pulse duration. So in the single polarization radars, even in the dual polarization, there we are using the two pulses. One is a short pulse and another is a long pulse. So short pulse duration is 1 microsecond. That is only for a small duration, the transmission takes place, and then the transmission stops, and then the reception takes place. Another is a long pulse, which has got the duration of 2 microseconds. I'm talking of the case when we are using the klystron or the magnetron kind of the systems are there. But for your information, nowadays, the solid state transmitters are available in the latest Doppler weather radar. And in those transmitters, there are 3 types of the pulses are used: a small pulse, medium pulse, and the long pulse. The small pulse may be of the order of 1 microsecond or 0.5 microsecond. For the medium pulse, it can go up to 10 microsecond. And for the longer pulse, it can go up to 95 to 100 microsecond. So why the different kinds of the pulses are used in the solid state transmitter? The meaning of this solid state means we are using the solid state technology. For example, the chips, what we are using, the mobile chips or the chips, integrated chips are there. So in that case, the technology is known as the solid state technology, which is coming on a large scale, where the klystron and magnetron will be replaced by the solid state devices. So this is the pulse width. Another is the pulse repetition frequency. How many pulses are transmitted per unit time? The number of the pulses transmitted in a given time, that is measured in the pulses per second, is known as PRF. Suppose we are transmitting 10 pulses in 1 second. 10 pulses in 1 second, we call it as frequency strain. If you are transmitting 100 pulses, frequency is 100. So what happens to the case when we are increasing the frequency here? You can see, if we are having the higher frequency, the range for the reception will be reduced. So when the frequency is more and more pulses are transmitted per unit time, then the range of observation will reduce. So we have to see later on in my next lecture, when the Doppler principle, when the unambiguous range and the unambiguous velocity will be there, there you will understand that when the pulse repetition frequency is more, then the time will be reduced, and then there will be the effect on its range, and then it can be discussed later on by my friends. So pulse repetition frequency is the second definition. Then the peak power. the maximum power of the pulse, that how much power is transmitted by the radar, is known as the peak power PT. The wavelength, the length of the radio waves transmitted by the radar, that is a wavelength, as we all know. The difference between the two highs or the two lows, crest or troughs, this is known as the wavelength. And the relation we know very well. The velocity c is equal to frequency multiplied by the wavelength. That is, wavelength and frequency are inversely proportional to each other. When the frequency is high, wavelength is low, and vice versa, where the velocity of the electromagnetic waves is same as that of the velocity of the light. And one more definition is coming here, the minimum discernible signal, MDS, that is also known as minimum detectable signal. See, when our target is around 300 kilometers, it's a small target. Even if you are sending the large energy to the target, there is a scattering phenomena. And because of the scattering in all directions, only a very small energy is coming back to the receiver. It means your receiver has to be so much sensitive that it is able to detect a very small energy, maybe of the order of 10 to the power minus 11, 10 to the power minus 12 watts. I'm talking of 10 to the power minus 11 of 1 watt. It means the MDS, that is a minimum detectable signal, is that capacity of the receiver which a radar receiver can detect a small signal very precisely. Yes, 300 kilometers away from the radar, there is a cloud which is containing the so many droplets and so on, so on. So MDS are the minimum discernible signal. This MDS is basically the quality of the radar or the sensitivity of the radar. More the sensitivity, more is the accuracy and the best good quality of the radar. So this particular parameter is very, very important, MDS. Another thing which I want to discuss is the beam width. What is the meaning of the beam width? That you can see from this diagram. So your antenna is like this. I'm going to the next one, this one here. Yeah. There is a parabolic antenna which is used in the radar. Remember, it is not spherical. It is not having the concave shape, but it is parabolic in nature. So the difference in the characteristics of a parabolic and spherical are there. Both are not the same, but parabolic reflector is preferred because whenever the parallel rays are coming on the parabolic reflector, they are meeting at the focus. Probably everyone knows very well that the parabola is reflecting all the rays which are coming to the from the front side. They are coming to the central part, and there is a feed horn. So this is the reverse phenomena. The feed horn is transmitting the energy from the center, and it is going in the form of the beam in the front direction. So if you see this particular image, you can see that there are the 3 balloon kind of the structures are there, one at the center and 2 on the other side. The central part, which is known as the main lobe, is containing the maximum energy, whereas the side lobes are containing only a small part of the energy. It means the maximum energy is going in the forward direction. So when the radar beam, it is initially pencil beam, but when it is going away, it is broadened here, it becomes widened here. And in that case, where the power is reduced, because when the power is going away, the strength slowly reduces. So at a particular angle, when the power is reduced to half, this angle between the 2 points of the main lobe is known as beam width, where the power is reduced to half. You can see here, we have written 0 dB, minus 3 dB, minus 10 dB, and so on. So minus 3 dB means power is reduced to half of the initial value. So main lobe is containing the maximum power, but on the sides, it is having the power half of the central power here, and it is known as the difference in the 2 parts is known as the beam width. Smaller the beam width, better is the resolution. So in the good quality radars, the beam width is of the order of 1 degree, or even if it is smaller than 1 degree, 0.9 degree beam width. Because in the case of the smaller beam width, a narrow pencil beam goes there from the radar, and it intercepts it is intercepted by the cloud, and it gives a very good information. So beam width is an important parameter for the radar antenna. Smaller the beam width, better is the resolution, better is the accuracy in understanding our target. The angle between the two directions on either side of the maximum, where the power density is half of that in the direction of the maximum, is called the beam width of the antenna. That is, in the central part, the maximum power is there, but slightly away, the power is around 3 dB down. That is, the power is half of the maximum power. So between these 2 points, because these 2 points are either on this side, on that side, as well as on the other side also. So it is basically the power in the form of a balloon, like a lobe, and it is a 3-dimensional lobe here. So we can take the horizontal section as well as the vertical section. In the horizontal and vertical, the beam width is the same, and it is known as horizontal beam width and the vertical beam width. Usually in the radars, both the values are same. I request all the participants to please note down the questions, and you can ask me once the presentation is over. In general, the horizontal and vertical beam widths are each of 1 degree. The beam width depends, now the question comes, on what factors the beam width depends, because this beam width is an important factor for the accuracy, for the better resolution. So its design should be done very systematically precise. So the beam width depends upon the wavelength of the radar, number 1, and the size of the antenna, number 2. It means the formula is phi, that is the beam width, is equal to 1.22 lambda upon d. If we are expressing the beam width in terms of radians, or if you are taking in terms of the degrees, phi is equal to 70 lambda upon d. And from this mathematical relation, you can see here, the beam width is directly proportional to wavelength, number 1. Beam width is inversely proportional to the diameter. What does it imply? It implies that if the wavelength is large, beam width is to be taken accordingly. But if you want the beam width is small, then if you have to make it small, then the diameter should be large. So larger the diameter of the antenna, beam width will be small, but it depends upon the lambda also, that is a wavelength. So we will do one small exercise later on, probably in this lecture, that what will be the diameter of the antenna if you are taking the 10 centimeter radar or 5 centimeter radar or 3 centimeter radar if the beam width is 1 degree. So let's see, this is the same thing here. If we take beam width is 1 degree, we are applying the second formula. Phi is equal to 1 and say S band. S band means 10 centimeter. So 1 is equal to 70 multiplied by 10 divided by D. So D goes on the left hand side. D is equal to 70 multiplied by 10 centimeter. That is a 700 centimeter. So the drop diameter can be around, not antenna diameter can be around 7 meters if you are doing this exercise. I'm repeating. If you take phi is equal to 1 degree using the second equation, 70 lambda is S band, 10 centimeter upon D. So we want to calculate that what will be the diameter of the radar antenna for S band. If you take it on the left hand side, 70 multiplied by 10 is 700 centimeter. That is a 7 meter. It means the diameter of a 10 centimeter wavelength radar will be 7 meter, around 22 feet. If you are taking the C band is 5 centimeter. Certainly, when the wavelength is reduced to half, for the same 1 degree beam width, the diameter of the antenna will be reduced to only, you can see, 3.5 meters. And if you are taking the X band, where the wavelength is only 3 centimeter, so 70 multiplied by 370, that is 210 centimeter, that is 2 meters. So in the case of the X band, for 1 degree beam width, the diameter of the antenna will be only 2.1 meter. It means a smaller antenna can be used in the X band, almost 3.5 meter in the case of the C band, and around 7 meter diameter antenna will be there, parabolic dish antenna in the case of S band. You can understand, if the size of the antenna is large, the antenna will be very, very bulky. So if you don't want to use it for the thunderstorm, so why to go with the S band? We can do this, get the same thing done with the X band or the C band, where we will use a smaller antenna. It will be lighter in weight. It will be cheaper in the cost. It will be easy to handle and so on. So in my last lecture, I had a discussion that the choice of wavelength is very, very important. For thunderstorm in the hilly area, we don't prefer C band or S band because they are bulky, they are very costly. And the range, because in the hilly terrain, the range is restricted to 100 and 150 kilometers. So why don't we use this X band, where the cost is around 1/10 of the cost of 1/5 of the cost of the S band and around 1/3 the cost of the C band. So the choice of the frequency or the wavelength is very important. What we want to see: a thunderstorm, a cyclone, a tornado, heavy rain, whatever is there, the strong winds. So we will choose either the X band or the C band or the S band. So accordingly, we have to design the system, and for the designing of the system, for good accuracy, the beam width should be either 1 degree or less than that. If you increase the beam width here, the resolution will be poor, and therefore it is preferred that the beam width should be around 1 degree. So this is to be understood by everyone who is dealing with the radar meteorology, that why it is so important. And a simple formula: phi is equal to 70 lambda divided by. There is another parameter which is very useful in the discussion of the radar meteorology, that is known as a antenna gain. Gain means how much is the amplification done by the antenna. We know larger the antenna, larger signals are coming to the antenna, and then it will amplify the smaller signals. So the gain is that how much it can amplify the smaller signals. The antenna which is receiving the signals plays a very important role, because this is the first item which is receiving the signals here. Then amplification by the receiver, and so on, so on. So what is the meaning of the antenna gain that we discuss here? It is defined as the ratio of the power radiated by directional antenna. Our dish antenna is a directional antenna. Whereas if you are taking a rod, a simple rod as an antenna which is transmitting this here, so this will be radiating in all directions. And this kind of the antenna are a small point transmitter is there. I'm talking of a smaller, say, iron metallic antenna is there. So that will be radiating in all directions. So that is known as the isotropic antenna, which is transmitting in all directions. And directional antenna is that one which is giving the direction of the electromagnetic waves in a one direction only. And this is known as the unidirectional or the directional antenna. So directional antenna transmits larger power, receives larger power, whereas the omnidirectional antenna that is radiating in all directions in a particular direction, the power will be less. So we are comparing these two. If there is a isotropic antenna which is radiating in all, and there is a directional antenna which is radiating in one direction, so if certain point we are comparing the both, so which will radiate more? Certainly the dish antenna or the directional antenna. So how many times it is transmitting as compared to a omnidirectional or a small directional antenna? This is called the gain of this dish antenna. I hope you know, in our house also, where the DTH is there or the smaller dishes are there, they are receiving the signal from the satellite. So if you are having the smaller dish, the signal strength is less. If you are using a bigger dish, signal strength will be more. So the same is the case in the case of the radars. So we are comparing this radar dish antenna with the isotropic or the omnidirectional. Omnidirectional means in all directions. So in a particular direction, we are comparing, suppose a particular direction is chosen and the same power is given to a point antenna and the same power is to the dish antenna, from which antenna this particular point will receive more power? Certainly from the directional antenna. So how much more power is transmitted as compared to the isotropic antenna? This is known as antenna gain, and it is expressed in the decibel and expressed as antenna gain in dB is equal to 10 log to the 10 power received from an antenna divided by power received from an isotropic antenna. In general, the gain of a parabolic antenna is of the order of 44 to 46 dB. Please remember, decibel scale is a logarithmic scale. It is not as simple as a multiplication, but in one of my lectures, I'll discuss that what is the meaning of the decibel, what is the meaning of 44 decibel, and many other things respect to the dB we will discuss. Probably you might have heard that the sound strength is measured in terms of the decibel. Our ears are sensitive with respect to so many decibel only. And if it is going beyond the decibels, particular decibels, this may harm our ears. So these are the things which are given in the terms of antenna gain. You can see here the parabolic dish antenna, and this parameter D, which you can see here on the left hand side, which is known as the aperture or the diameter of the antenna, and in the front side the feed horn is there, which is connected to the transmitter. So from the feed horn, the energy is incident on the antenna. So when the energy is going in the front direction, when it is reflected back, it is going in the forward direction, and it is coming in the form of the parallel rays, and it becomes a smaller, a pencil beam kind of the system is generated here, which is going in the form of the lobe, and then it is moving in the front direction. So this is the antenna and its related things here. Now I'm coming to the radar range equation for extended target. Why I'm using this extended target? Because our cloud is not a point target. It is an ensemble of millions and billions of the small droplets. They are moving randomly in the different directions. So these drops are basically the point target. But overall, this cloud is basically a system of ensemble of so many millions and billions of the drops here. So we are calling it as extended target. Radar range equation is very, very important equation, whether it is a radar meteorologist in the manufacturing part or radar meteorologist for the analysis part, for both the persons. This is important here because it gives many things to understand. So radar range equation, range means till how much range, how much distance radar can have its measurements. Because once the our target is going beyond that particular range, so your system will not be able to receive the signal sufficiently large to understand and to analyze it. So this radar range equation is dependent on so many parameters of the radar, which I'm going to discuss in the radar range equation. I'm not giving you the proof because the proof is slightly complicated and it's not required for everyone. It's available in the books here, but I'm giving the final equation. So this equation is used by the radar meteorologists, radar manufacturers, and scientists to calculate the receipt power by the receiver of the radar, to analyze the radar echoes received after the backscattering phenomena due to hydrometeor, water drops, hailers. I request all those who are raising their hand, just please wait. After 5 minutes, we will have the question and answer session about for 30 minutes. So you need not to worry about the questions. I'll try to reply all your queries. So the equation is PR is equal to PT H capital G square phi theta pi cube modulus k square summation d to the power 6 divided by 1024 log 2 lambda square r square. And now we can replace this summation d to the power 6 by z. So the second equation is there, and this equation is very, very popular and useful. So what are the terms which are being used in this? I'm showing in the next slide. So this equation is to be remembered. Why do I say remembered? That the received power by the antenna, I'm repeating again, the received power by the antenna is dependent on so many parameters which we are going to discuss now. This is the system here, that how a particular target or the sampling volume is taking the observation with respect to the radar beam. I'll request once again, please, you can have your questions. You can note down all the questions, and I'm going to reply after 5-7 minutes after the end of this presentation. So this is the sample volume. It is a 3-dimensional volume. So we are considering in terms of this r, theta, and phi. Radar beam is going there, and it is taking the observation of the sample volume, and you can see this r. This r is nothing but the range which you can see here. Small r I'm talking about. Capital R is different, basically. So small r is the slant range, and here capital R, these are the basic points, P, Q, R, S on the 4 sides of the sample volume. So this is the way in which the radar equation is used here. And now this is the explanation of the terms which are used in the radar range equation. PR is the power received by the receiver of the radar, measured in watts. Wait. I'm sorry, this. Dr. Vilash, my presentation got closed immediately. I don't know what was the reason, but now I started again. Are you able to see it?
Yeah, yes, sir.
Okay. Yeah. My laptop suddenly went in this blank mode.
Okay, now it is coming. Yeah, we can.
Okay. Okay. Thanks, man. Thank you. So I was explaining about this different terminologies used in this equation. PR is the power received. PT is the peak power transmitted by the radar. That is again in terms of the watts. H is known as the pulse length. What is the significance of the pulse length that we can discuss? That it is the product of C and tau. C is the speed of the electromagnetic waves, that is 3 into 10 to the power 8 meters per second, and tau is the pulse duration or the pulse width. So product of C and tau gives us the pulse length. So pulse length is basically the multiplication of velocity as well as the time. So unit is in meters. G is the antenna gain. Larger the antenna gain, larger will be the received power, because you can see in this equation, this received power is directly proportional to PT, transmitted power, directly proportional to H, directly proportional to G square, directly proportional to phi, theta, directly proportional to K square, directly proportional to d to the power 6, but inversely proportional to wavelength square and the range square. So this equation is very, very useful. Larger the antenna gain, the received power will be large because it is G square. Larger the transmitter power, 100 kilowatts, 200, 500, 1 megawatt, and so on. So this equation gives a lot of information that on what factors the received power, the sensitivity of the receiver depends. Phi, horizontal beam width, theta, vertical beam width. Capital K is related to complex index of refraction. It has no units. Capital D is the diameter, R is the range, and lambda is the wavelength. So this is basically the introduction of the radar range equation, which is very, very important to know by each one of us. I'm coming to the last few slides. Then we will start our question and answer session. PPI, somebody asked me last time that what is basically the plant position indicator. So here I show you this particular diagram here where you can see that at a particular elevation, when the scanning is done in the 360-degree rotation, it is called PPI. It is gathering the information at a particular elevation. The elevation can be 0.2 degree, 1 degree, 2 degrees, etc. But that elevation is constant, and then it is taking a 360-degree rotation here, and it is capturing the information related with the clouds. So this is basically the PPI, and it is giving us the information in all three directions. So plant position indicator is obtained at a fixed elevation by azimuth scanning of the antenna for a selected range of observation. It shows all echoes received in the radar range. In a particular elevation, wherever the echoes are there, it is showing in the form of the 2D image. The intensity of the echoes is expressed in the dBz. Now, what is dBz? That we will discuss afterwards. Decibel with respect to the reflectivity. So when the radar reflectivity factor is there, it is converted into the dB, and it is called dBz. PPI is useful in weather surveillance of all kinds of the severe weather activities, depending upon the range of the target and the angle of elevation. Angle of elevation, if you are taking more, so only a small information will be there. So usually PPI is taken at 0.2 degree or even 1 degree elevation of the antenna. We cannot make it along the horizontal because in this case, so much of the ground clutters and the obstruction will come. So usually it is 0.2 degree or 1 degree or 2 degrees, depending upon the terrain conditions, because in the hilly region, when the surrounding mountains and the hills are there, we cannot keep it 0.2 or 1. We have to make it sometimes 2 degrees or 2.5 degrees. So range reduces when we are making the elevation angle large. The nearby echoes correspond to lower altitude, whereas the farther echoes correspond to high altitude, depending upon the range. So this we can understand that how the elevation is taking place in this case, and at a particular elevation, then 360-degree scanning is done. This is called PPI. This is an image from the Doppler radar from Kolkata on 7th May 2010, a quite old picture, but I'll show you the latest one in my next lectures, the latest images here. So we can see here at the center of this image, where the KOL, that is a Kolkata, India, is there, and the circles are there. Each circle is having 100, 100, 100, so 100, 200, 300, for a 500 kilometers range. PPI is able to get the information, and these are the images of the clouds in all directions. And on the top left-hand side, you can see it's given here, the file name 2010-05-07, that is 7th May 2010. And this is the time of observation, 10:52:41 in UTC. Type is PPI, Z means reflectivity. If it is a velocity PPI, it will be PPI-V, and the range of observation is 500 kilometers. So for today's lecture, this is enough, where I have started with the scattering, the different kinds of the scattering. Why do we prefer this Rayleigh scattering? What is the equation related with the Rayleigh scattering? And then we came to the radar range equation and so on. So for my timetable, my second lecture was limited only up to this point. And my friends will take the next lecture after this, that what is the Doppler principle and unambiguous range, unambiguous velocity, different products, and so on. So thank you very much for listening my lecture here till this point. And I request the admin to continue the question answer session.
Thank you very much, sir, for a wonderful lecture on the basic parameters related to scattering and the basic radar equations and other radar parameters relevant for radar equations and all. So this session is now open for discussion. I request Swagata and Lakshmi Kumar to handle this Q&A question and answer session.
Dr. Abhilash Swagata is not there, so I'll take over.
Yeah, thank you. Please, Millie is here, right? Millie or Rohini? Both.
Yeah, this is
Yeah.
Rohini. Okay.
Okay.
Yeah.
Rohini, please.
Dr. Rohini, you can continue.
Yeah, thank you, sir, for such a nice lecture. The first question is, can we say that the pulse width is nothing but the observed data we get from radar?
No, pulse width is related with the transmitter here, that for how much time the transmission should take place here. So pulse width is not directly giving you the information that how much data we are getting out of that. It is basically the time for which transmission is allowed, because after that transmission is stopped, and when the transmitted signal is going, we provide the sufficient time for the signal to come back and for the analysis. So pulse duration or the pulse width is basically when the transmission continues and after that it stops.
From the same person, which is Archana. So she has asked another one. For different purpose or meteorological phenomena study, we need to use different radar. This is the first question.
We have to use the different radars.
For different meteorological phenomena.
Yes, it is. In my previous lecture, I said the choice of the X band, C band, S band, L band, K band, whatever be the type of the radar you are using, you have to choose the particular meteorological phenomena. For example, if you want to use for cyclone detection, for the heavy rainfall detection, X-band radar is not advisable, because in the X-band radar, lot of attenuation and the absorption of the signal will be there. So either C-band or S-band will be preferable for the cyclone and the heavy rainfall. On the other hand, if you want to go for the thunderstorm, hailstorm detection here, in my opinion, X-band is the most suitable, because in the X-band, the size of the wavelength is 3 centimeter. So 3 centimeter is best suitable for the thunderstorm, hailstorm, tornado, etc., but not for the cyclone and this. So obviously there is a selection of the particular wavelength or the frequency depending upon the observation of the meteorological phenomena.
Another one she asked was, one radar will not give us information of all phenomena. That is because of wavelength. I think you answered the question.
Probably a single radar can give you all this information, but up to what extent it will be correct, accurate. For example, if you want to use S-band for all thunderstorm, heavy rainfall, cyclone, everything, S-band can be used alone, stand-alone for all kinds of the phenomena. But when the wavelength is 10 centimeter for S-band, there will be an overestimation of the thunderstorm or the rainfall. Similarly, if you want to use X-band for every phenomena, for cyclone, the information will not be available because the absorption of the X-band will be there. High frequency attenuation will be more. So S-band you can use, C-band you can use, but in my opinion, S-band is very, very large and it is give a lot of overestimates for the thunderstorms. Cyclone it is good, but thunderstorm it's not good. So why don't we use C-band? C-band is a good compromise between X and S. C-band, neither it is too large, nor it is too small, nor too much of attenuation is there, nor overestimation, not underestimation is there. So in my opinion, C-band Doppler radar will be the most useful here. And if there is only one kind of the system is there, whether it is in the Himalayan range or in the plains or wherever is there, C-band is the most useful. This is my recommendation. But many scientists say X-band is good for the thunderstorm, C-band, S-band good for the cyclone, etc. So it varies from person to person. But my opinion is that C-band is the most useful, most economic, occupies less space, and it is versatile, able to provide each kind of the information.
There are two questions from Shuib. The first one is, what is the smallest size of raindrop that can be detected?
Usually 0.5 millimeter diameter, 0.3 millimeter diameter can be detected here, because if the drop size is smaller than that, this will be slightly difficult. But I say we are not going to see the individual drops here. We are going to see this extended target here, where the ensemble or the collection of their drops are there. So bigger the drop, bigger is the reflectivity, because drop diameter to the power 6 gives the reflectivity or the radar reflectivity factor. So smaller drops contribute less, and one bigger drop contributes tremendously high. Because if you are taking 1 million drops of the order of 0.5 millimeter diameter and one drop or 10 drops of the order of 1 centimeter or 5 millimeters, then the contribution will be tremendous by the bigger drop, because it is d to the power 6. So power 6 plays an important role. But individually, if we see the smaller drops of the order of 0.5, 0.1 millimeters can be detected here. But in the case of the meteorology, we are not going to identify each and every one here. It is the ensemble, that is the extended target is there.
Sir, another question by the same person. What is the smallest size of sampling volume which is considered the occurrence of rain?
This depends on the so many parameters. Sample volume is your cloud. Sample volume may be the part of the cloud where the radar is getting information from the particular cloud. So what is the vertical extent? What is the precipitation content? What is the horizontal extent of the cloud? So all these things to be seen here, but the most important parameters are two. One is how much is the precipitation content, rainfall content is there, number one, and how much is the vertical extent. The height of the cloud is very important, because larger the cloud, more will be the intensification, more will be the precipitation, more will be the downdrafts, and more will be the rainfall rate. So we have to see all these things combinedly together.
Next question is from Anonymous. Suppose I have radar pixel image with different colors representing rainfall rate. Is it possible to work backward and find parameters of ZR relationship? If yes, how to proceed?
Yes, you can do it.
Then he's asking how to proceed.
Basically, if you are doing this image processing here, so you have to find out the different colors are the different pixels are the group of the pixels, and then you are converting into the rainfall here. That can be done, but the most important thing is the validation by the actual rainfall. Because radar gives an estimate of the rainfall when the cloud system is there in the sky, but when all the rain is coming to the ground, the rain gauge is the most suitable, which gives you the information that how much rainfall has taken place, provided the overall cloud should be over that particular rain gauge here. So by image processing, you can get an idea, but ZR relation is to be seen here with the help of the validation or the comparison by the rain gauge. It's not easy. A large population of the data is required here. And one of my papers is there where I have shown that how ZR relation is evaluated. Evaluation of the ZR constant over Kolkata. This is the title of my paper. There they can see that what is the overall process here. And we have to collect so much of the data in that.
So next question is from Govinda. How the radar differentiate the low level and high level clouds?
How the radar differentiates?
Low level and high level clouds.
Yeah, because you are getting these images here where you can see the base of the cloud. There are the two products, not two products. There are so many products in the radar here, Doppler radar, where the base of the cloud is one of the products, top of the cloud is there, and the overall maximum reflectivity, that is a MaxZ image product, is also there. So if you want to take only the base of the cloud, this is one of the products. It is known as E-base. E-base means eco-base. So you can find out that at particular reflectivity level, what is the low cloud, what is the base of the cloud. And when you are going for this top of the cloud, that is known as E-top. E-top, E for eco, and top means maximum echo, the height of the maximum echo. So there you can find out that what is the base, what is height. But there is one image which is known as the maximum reflectivity, max Z, where you are looking for this entire vertical development of the cloud, horizontal extent here. There you can easily find out what is the low level cloud, what is the higher level cloud. So distinction is 100% possible by radar.
Next question is from Jagdish. Why do we express radar return in dB?
Why do we express radar?
Radar return in dBz.
Okay. Extended target is there, meteorological volume, say cloud is there. Now this particular cloud is containing very small drops, 0.05 millimeter diameter, 0.1 millimeter, and there is a large number of the drops there up to say around 1 centimeter. So it is receiving the signal from all these. So in that case, what happens? The reflectivity is varying because it is Z is equal to summation d to the power 6. Summation means it is summing up. It is taking the summation of 6th power of the diameter. So we are taking 0.01, 0.02, 0.1, 0.2. So there is a big spectrum with respect to the Z, and being a 6th power, the graph will be exponential. It is going low. So instead of going for this exponential graph and the large number of the Z values, we are taking a logarithmic scale, log Z. And when we are multiplying by 10, it will become 10 log Z. And 10 log Z is termed as dBz. So logarithmic scale, as you know, it is a linear scale. For example, if you are talking about x to the power 3, if you take the log, this is 3 log x. So 3 log x, it becomes a linear. Similarly, a into b into c, a multiplied by b multiplied by c, it is multiplication. You take the log. Log of y, suppose, is equal to log a plus log b plus log c. It becomes linear. To make the scale linear, the reflectivity is expressed in terms of dBz instead of z.
There is another question by Anonymous. What are those blue lines seen in PPI image in the last slide?
Last slide, that is around, I think, the question is related with the
blue lines.
PPIZ.
PPI image, yeah.
This one.
The blue lines.
So you're talking, this question is related with the straight lines, blue straight lines, or the cloud which is shown in the blue color?
No, sir, it mentions about lines actually.
Oh,
maybe these lines. Yeah.
This is basically the noise or the interference from another source.
Okay.
These are not the cloud echoes. These are some interference because of some microwave station or some other source from where the some interference is created in the radar. So these are those lines. These are the noise and maybe neglected. Basically, the cloud structure is not very symmetrical like a line, not so this kind of the steep kind of system. These are the other ones which you can see in the form of the some blue patches there, or some line is there in the different colors, orange, yellow, white, blue, etc. So these are the what should I say, interference or the noise from some external source.
Okay. Next question is, can you explain application and principle of plan position indicator?
Yes, it is. The principle is that we are keeping a particular elevation constant, which you can see here in this image. Here on the right bottom, it is given EL 0.2 degree. That is, elevation is 0.2 degree and azimuth is 0 to 359, that is 360 degree. So at a particular elevation, it is taking a round, circular round of 360 degree and gathering all information. So the application is, this PPI is able to provide the location of almost every cloud in the all directions. Here you can see here in the north, in the northeast direction, in the south direction, all the clouds can be seen and its precipitation content can be find out easily here that what are the different clouds available in the different directions. And the range is around up to 500 kilometers for S band. So this is plant position indicator, which is showing the availability of the clouds in 360 degrees all over the radar.
Next question is from Ilyas. Is there a maximum and minimum size of radar antenna?
Maximum and minimum size of the radar antenna.
Yes.
Basically, the size depends upon the two parameters. What I have shown you, if you remember this formula, phi is equal to 70 lambda upon d. D, that is the diameter of the antenna, which decides the size of the antenna. So this depends upon phi, that is the beam width, and depends upon the lambda wavelength. So if 1 degree is the beam width, d is equal to 70 lambda, it means we cannot say what is the minimum size, the maximum size. It depends upon the wavelength used as well as the beam width requirement. In some cases, when the beam width requirement is not 1 degree, say it is 2 degrees or 3 degrees, where the resolution is not much required. So accordingly, you can calculate that what will be the size of the antenna. But remember, we cannot say what is the minimum or maximum. We have to make it optimum based on lambda and beam width.
Okay. What software used to calculate different equations? Example, ZR relation.
Oh, any software. ZR relation is a simple calculation. There is nothing like that. You can use anything here. But nowadays, all these things are available in the radar itself. Just you click on this Z and the value of R is coming, and there is one product in the radar that is known as SRI, Surface Rainfall Intensity. It is automatically converting the reflectivity into the rainfall rate. So it is a directly available product.
Another question is, in which file format radar images are stored?
There are so many file formats. NetCDF is there, SDF5 is there, and so many other formats are there. But it depends upon a particular radar. Now, present radars are whatever are available. They are having their own system software. For example, from the EEC radar, they have got their own system. From the Indian radars, Bharat Electricals and Astra Micro Limited are some more data patents, etc. They are having their own system software, but they are convertible into the other SDF5, NetCDF, then some more data formats are available. So data conversion, format conversion is easy now. It's not a big problem nowadays. So whenever anybody wants the data in a particular format, they have to write to IMD. IMD on their request for the research will provide the data in that particular format. Otherwise, NetCDF format is the most powerful format available for the radar data.
Okay. The next question from SVJ Kumar. What are the limitations of positioning different radars C, X, F in the same location?
Since they are operating in the different bands, no problems. One example is New Delhi. New Delhi is the only place in India where all the three kinds of the radars are there. X-band radar is there, C-band radar is there at Mausam Bhawan, New Delhi, and S-band radar is also there. So since their operating frequencies and wavelengths are different at the same location, you can use all together. There is no problem.
Next one is, can we convert existing radars to dual polarized radars? How to do it?
Yes, yes. This process is going on in India Met Department, where the old radars are getting converted into the dual pole, because in the single polarization, only one type of the horizontal polarization is used. So you have to use the another type vertical polarization. The hardware is different. In place of the one waveguide, you have to use two waveguides. And there are the two horn feeds, one for the horizontal signal and one for the vertical signal. So hardware is to be changed, software is to be changed, but this is 100% possible that you can change the single polarized radar into the dual polarized radar. And many countries in the world, they are switching over from the single polarization to the dual polarization, because dual polarization has got many advantages over single pole. Probably my other friends will be discussing over this dual pole systems.
Next question is, from Jagdish. Thank you for the interesting lecture. I have few doubts. Is there any way we can calculate vertical wind speed?
We can calculate vertical wind speed.
Yeah, that's the question.
No. For vertical wind speed, you have to go for the wind profilers, because the wind profilers can give you the idea about the three-directional wind, and there you can get the true winds. In the case of the radar, you are getting only the radial component of the velocity. Radar does not give the true winds. It is only the radial component. If the true wind is V, say V, then V cos phi will be the radial component here. Since cos phi has got the maximum value 1, but all other values are less than 1. So the winds, what we are getting from the radar is basically lesser or at the most the true velocity of the wind. But vertical winds, we cannot get. No.
Another question by the same person. What product Marshall-Palmer equation gives? Is it surface precipitation amount or amount of rain particles in that volume?
Please repeat the question.
What product Marshall-Palmer equation gives? Is it surface precipitation amount or amount of rain particles in that volume?
Basically, radar is looking for the clouds in the sky. Suspended particles are there, and not every particle is coming in the form of the rain. So if you are going to see that how much rain is actually taking place on the ground, then around 80% of the radar estimate is good here. And we have to see the rainfall when it is coming to the ground here. So either the rain gauge or the product, the surface rainfall intensity, that is to be seen here. But the validation is very much important for the radar.
Is there a reliability issue of the weather radar?
Repeat again. Please repeat.
Is there a reliability issue of the weather radar?
What reliability means?
I also didn't get reliability means maybe if they are reliable or not for the
Okay. See, radar is looking in the sky, sending the electromagnetic waves. So no meteorological phenomena can be escaped from this. It is very much reliable. But reliable in what? It can see a particular cloud, its dimensions, its size, its shape, its precipitation content. All the things are very reliable, and tracking is also reliable. Wind is also reliable. So if you are using the word in terms of the reliability in monitoring and tracking, 100%. If you want to know about the true winds, around 80-85%. Actual rainfall, it is again 85 to 90%, because radar is looking in the sky where the suspended rain is there. It is not the 100% which is coming to the ground. So reliable in the sense, tracking 100%, moving the system 100%, winds 90%, the rainfall around 90%. This is the percentage of the reliability.
Okay. Next question is by Dr. R. Mahesh. When we select the location for radar installation, how pulse wavelength plays important?
When we are finding the location for the radar installation,
how pulse or wavelength plays an important role?
Yeah. See, pulse has nothing to do with the location of the installation. Wherever you install it, pulse determines the velocity and the range. That is the pulse duration and the PRF, pulse repetition frequency. But for the location of a particular radar, whether it is in the plains, or it is at the coastal station, or it is in the hilly area, or it is at some another place here, the wavelength is very important. Wavelength 3 centimeter for X-band, it is good for plains, thunderstorm, hailstorm, etc. Good for the hilly area, for the rain, moderate rain, and even heavy rain can also be estimated up to a certain extent. So wavelength is the main criteria for choosing a particular location and a radar.
The next question. C-band with 5.6 gigahertz can see dust.
Can see
Dust.
dust.
Yeah.
See, dust storm is tracked by many radars, even by X-band and C-band radar. So when the dust storm is there, it is having a different pattern, different observation, and the reflectivity is again different here. The precipitation content cannot be there, but the dust storm can be seen by the C-band radar. And my opinion, X-band and C-band both can see it. Even S-band can also see it. But as I suggested earlier, C-band is the best compromise among all, cost-wise, location-wise, observation-wise, data-wise. For everything, C-band will be the best. But some people prefer X-band over C-band for dust storm and the thunderstorm. So C-band is capable.
Okay. Next is, if I want to build a radar for wind measurement, what are the crucial factors to consider while designing the radar system?
For
wind
wind,
measurement.
wind measurement.
Yeah.
Basically, if you are looking for the winds here, true winds here, or the best quality of the winds here, radar is not suitable. Because radar is giving only radial component, and radial component can be sometimes 60%, 70% of the true winds. So if you want to have the good quality of the wind observation, you have to use the wind profilers, nothing else. Wind profilers are the best for the wind measurements, but radar, and that is giving the vertical profile, and over a smaller area you can get the wind information. You are getting all components of the winds and many other things related with the winds. The wind profiler is the best. Radar, I don't recommend. Radar for the weather phenomena observations over a larger range. Wind profiler is vertical and over a smaller range. Whereas radar is basically for the tracking of the thunderstorm, cyclone, hailstorms over 200, 300 kilometers, where wind profiler cannot be used. So wind profiler has got its limitation, but application in the wind measurement is the best.
Next one is, how those radar figures get analyzed and how those images explained to a layman.
The analysis of the radar images will be done by other experts of radar meteorology. And after my lecture, Dr. B.K. Kannan will be the person who will be explaining the different base products and the derived products here in my next lecture on 15th. So they will be explaining that these are the different products and how the analysis can be done. But my lecture is there probably in the month of July, where I'll discuss the actual movement of the thunderstorm sequences, how they are moving, how we can find the initiation, movement, speed, different kind of the thunderstorm system, single cell, multiple cell, and so on. So that I'll discuss in the next, but my other friends will be discussing about the reply of your question here, that how the analysis of the images can be done.
Whether the vertical distribution of different hydrometeors can be obtained from radar.
Please repeat again. I just want to listen again.
Whether the vertical distribution of different hydrometeors can be obtained from radar.
Vertical distribution can be seen by the radar images here, but probably you can see because when the height increases, there are the snows, snowflakes, hails, and many other things are there. Sometimes the bright band is also formed at a certain height. The bright band that we'll discuss later on, what is that? So many phenomena can be seen in the vertical direction. It is possible only within the clouds.
For dual polarization radar, the observed drop size. That's the question. For dual polarization radar, the observed drop size.
See, drop size distribution and other things cannot be given as a standalone system that it is there, because when the radar is there, it is not looking for a single drop or few drops only. It is looking for a bigger sample volume which is containing large number of the drops. But they can distinguish that there are so many bigger drops are there, large number of the bigger drops, and say some small number of the smaller drops, and so on. But for a particular drops, you can say 1 centimeter, 2 centimeter can be there. But dual pole radar is basically to distinguish between the water drops and the snow or the hails. For the detection or the distinction between the water drops and the hails, the dual pole system is very good. For finding out how much is the rainfall will be there without zeta relation, dual pole system can provide very good information from its product that you will see later on.
I needed to ask CUSAT team. There are still 5-6 questions. Should I proceed? Sir, is it okay if I proceed?
Please.
Okay.
Another 5 minutes.
Okay, sir. Next question. If it covers in such a way and a country have enough radars covering, does it is necessary to have conventional stations to collect and give forecast? Maybe he means that if the enough radars are there for a country to be covered, then is it necessary for conventional stations?
See, nowadays mosaic is formed when we are having so many radars and which covers the entire country. In that case, from all the radars, the information is received at a central location, and then they are creating a mosaic. Mosaic means they are taking the radar information as per the latitude, longitude of that area, and then it can be put over the GIS map. So when the GIS map superimposition is there, and then it is projected here. So all information is coming in a one picture itself. Or otherwise, when independently the stations want to use that particular information, that can also be used. So both ways, either in the form of a mosaic or in the form of form of an independent use here by some user here. Both are possible here.
Next one is radar echoes same as radar image?
Radar echoes same as radar?
Image.
Radar?
Image.
Yeah, basically image is the bigger one, which is showing all the radar echoes. So radar echoes are presented in the form of the image, in the categorizing in the form of the different pseudo colors. Starting from the blue, then it is going to the white, light yellow, orange, then red, deep red, etc. So these are the pseudo colors which are generated as per the precipitation content inside the radar echoes. So radar echoes are presented in the form of the image, that is true, but in the form of the different colors which are generated by the computer. Different colors are generated.
How much we can rely on Marshall-Palmer equation? Is it, if it considers all hydrometeors present in a column?
Marshall-Palmer relation, in which A is equal to 200 and B is equal to 1.6, is a generalized relation given by Marshall and Palmer. They suggested if you are unable to calibrate the different values of A and B for that particular place, please use it, because in most of the cases it is suitable. There will be some variations in 200 and 1.6 for A and B. Somewhere it is 190, somewhere it is 1.45, etc. But if calibration is not possible for getting the new values, use this 200 and 1.6. It's a good generalized formula.
Next one is minimum observed drop size by dual polarization radar.
As I earlier said, that for the individually, we cannot say that it is what is the minimum size. It is basically the group or the ensemble collection of so many smaller drops, bigger drops. So maybe very small drops are there, but when we are coming in the form of the sample volume overall, so everything is coming here. So you cannot say that it cannot detect this one or the. It is not the individual drops. It is the group of the drops, water drops, hail, snow. So what is the overall contribution with respect to the rainfall? How much total is there providing the rainfall? It is basically the radar echo.
Okay, sir. And next one, how to filter the noise echo due to interference from output image?
Yes, there are so many software returns here where the attenuation is given. Some it is due to the hardware as well as by the software. Some filters are designed. Filters are basically the software programs that filters out all the unwanted signals, ground cluttering, what should I say, the stationary echoes, the angel echoes, bird echoes, and many other things can be filtered out. So software programs are there just to remove the unwanted echoes.
How satellite-borne radars work?
Satellite-borne radars are working on the same principle, but their beam width is large so that their size of the antenna is smaller. In the case of the TRMM satellite, there was a space-borne radar, satellite-borne radar that was known as a precipitation radar. It was working in the C-band probably, and it was having a smaller antenna, so it is having the same. Only the difference is radar is basically, our radar is a ground-based radar. It is looking from ground in the sky, and that space-borne is looking from the satellite to the radar, to the sky. So both the principle is same. There is no difference. Only the looking way of looking is different. Ground-based radars are looking from the ground, space-based from the satellite, but principle is the same.
Okay, sir. Next one. Which satellite imageries can be related to radar reflectivity?
Yeah, there are so many papers by the researchers. They try to correlate because the satellite also gives its images in the form of the precipitation itself. So during the daytime when they are having this images as well as in the IR images in the evening time, night time. So they are looking for the same thing here, but the difference is there that satellite is looking from the top, and the principle is slightly different. Here radar is active and it is sending the electromagnetic waves, and the electromagnetic waves are coming back. In the case of the satellite, the imagers are there. They are receiving the signals from the surface of the clouds, but transmitters are not transmitting. Satellites are not transmitting anything. They are the channels which are receiving the images, the infrared signals and the reflected signals, which are known as the albedo from the particular target, and so on. So this is slightly difficult, but some people are trying that how the radar reflectivity and the satellite images can be correlated. There will be correlation. More the precipitation, brighter will be the satellite echoes, and better will be the echoes in the radar. So there may be a correlation, but one-to-one correlation is slightly difficult.
Next one is how a reflected component from a meteorological target and a transmitted component from a distant radar can be differentiated.
Once again, please.
How a reflected component from a meteorological target and a transmitted component from a distant target, distant radar can be differentiated.
No, I am unable to understand this question.
Sir, how a reflected component from a meteorological target?
Reflected component means the reflected signal only.
Yeah, and a transmitted component from a distant radar.
Transmitted component, see in the
From a
transmit
distant
from the
radar.
different, see when they are working in the different wavelengths or the frequencies, they will not interfere. From one radar, when the received signal is there, it will be analyzed. But when the signal is coming from the another radar, transmitted component means nothing. Basically, the electromagnetic waves are there of a particular frequency. So they might create interference only. What you have seen in that particular image here, these are the interference due to some another radar. Yeah, these white strips are, blue strips are there. These are the interference, but you don't have anything like transmitter component, nothing.
Next one, sir. Maybe last two we can. Can we detect the cloud fronts or frontal air masses and determine the frontogenesis process?
No, I'm not sure about this question.
Next one is, sir, can we use DWR to track sleek aircrafts? What about drone tracking?
Can be done, but for aircrafts and the drone is a smaller aircraft, nothing more than that. So these moving objects can be tracked, monitored, and ranged. Everything can be done by Doppler radar, but our Doppler radar is a weather radar. They are the tracking radars where the wavelength is different, their antenna is different, their software is different. So tracking radars are there, which are used by the defense and for the other purpose. So Doppler weather radar can see it, but see the target is bigger, drone is bigger, and the wavelength is 3 centimeters. So we are not going in the Rayleigh scattering, we are going in the Mie scattering. So that's not possible by the weather radar. However, you can see it, but processing cannot be done because the entire algorithms are different.
Sir, a quick last one. What is the difference between Rayleigh and Mie scattering? It was not clear for the attendee, so he wants to know it again. If you can.
Right. When the size of the target from which the back scattering echo is there, if the size of the target is smaller as compared to the wavelength of the radar, then Rayleigh scattering is applied. Example, our weather radar. Even if you are using X-band 3 centimeter, the particle size is 1 millimeter, 2 millimeters, 3 millimeters, 5 millimeters. So the wavelength is large and the size of the target is small. So Rayleigh scattering is applied, and we apply that the back scattering cross-sectional area is energy is 1 upon lambda to the power 4 and d to the power 6. This is Rayleigh scattering. When the target is bigger, wavelength is smaller, as the previous question. Drone is bigger, say its size is around 5 feet or 4 feet, whatever is there. Even smaller drones are there. So in this case, our wavelength is smaller, size is bigger. So Mie scattering is used, but Rayleigh scattering will be used in the weather radars. This is Mie and Rayleigh. Is this okay?
Yes, thank you, sir.
Yeah.
This was really a nice lecture, and I also enjoyed it. So back to the CUSAT team.
Dr. Rohini, just one question is from YouTube, and sir has given excellent explanation. That is why we are getting questions today. So too many questions. Sir, one last question, sir. Why receiving pulse duration is more than transmission pulse duration, and what are the parameters considered for this?
Okay. See, in the transmission, we are transmitting the energy like a burst. The energy is gone. So the energy is going, say, around 250 kilometers and so on. So when the electromagnetic waves are traveling, say, around 250 kilometers transmission, and then from the target, it is coming back 250 kilometers for the reception. Now, before transmitting the next pulse, you should wait that what is the received signal after the first pulse transmitted there. And then its analysis is also done by the receiver here. So we are giving some time for the reception here, but for the transmission, only a small burst is there. So usually the transmission time is only 1 microsecond, 10 to the power minus 6. But the reception time is in millisecond, where the signal goes, signal comes, and analysis is done. Once it is done, then the next pulse. Then again, more time for the reception, then a small time for the transmission.
Yeah, thank you, sir. Thanks a lot for excellent explanation.
Thank you.
Okay. Over to Dr. Abhilash, sir.
Yeah, thank you very much, Pradhan sir, for this elaborative session. And I think there are many more questions in the chat box and the question and answer session, but I think Dr. Rohini and Dr. Mie has done a great job in reading out the relevant questions and overlapping questions without much duplication. So it was a very wonderful and enlightening lecture. And after that, we all enjoyed the question and answer session more, because you have elaborated very fine details, and it is helpful for those who are going to work in the field of radar meteorology. So it's a foundation, and you have done that foundation in these 2 lectures, and I hope that other lecture will be in continuing to this. The attendees will get more idea about in the coming lectures, and it will be wonderful. It was a very nice session, both the lecture and the question answer session. We have learned a lot from this, and thank you very much. So now I think photo session we missed, and now we can have a brief photo session. I request all this panelists to turn on your video. Srigala is there, and Rohini, Dr. Rohini, and Srigala.
But I don't know what is happening. You can go ahead.
Yeah. Maybe we can take a photo now.
Your video is visible, Dr. Rohini.
Yeah, now it is visible. Yeah. Only Srikala and Mohan Kumar Das is left. So we can have the photo now.
Yes.
Aditya. Ready? 3, 2, 1, go. Yeah, Mohan is more expert in this. Yeah. So I think before moving towards the vote of thanks, I request Agisa to have some concluding remarks on this, and I request after that I request Ms. Chadushka Pramachandra from Meteorology Department, Sri Lanka, to propose the formal vote of thanks. Please, please. So your mic is muted.
Thank you, Abhilash, and you have summarized, I think, the lecture very well, and especially the question answer session. Really, Dr. Pradhan has covered from basics to the applications with examples so elaborately and in a simple language, and I'm sure all participants must have benefited. As we are going to put this PowerPoint presentation, and YouTube will be available for participants to follow it up further, and I'm sure Pradhan Saab will be ready to answer your things. You can always email and get in contact with him for further update yourself. So keep all these lecture series is going to give you a lot of relevant material related to the radar meteorology and its application both in forecasting and research. So make full use of it. Thank you.
Over to Ms. Chadushka.
Thank you, Abhilash. Thank you, Dr. Abhilash, esteemed guests, distinguished speakers, and respected colleagues. As we conclude this insightful and enriching session, it is my honor and privilege to extend a vote of thanks on behalf of South Asian Meteorological Association, the Advanced Center for Atmospheric Radar Research, and Cochin University of Science and Technology, India. Firstly, I express our deepest gratitude to Dr. Mohan Kumar Das, the Joint Secretary of SAMA and the Executive Director of National Oceanography and Maritime Research, Bangladesh, for his warm welcome address that set the perfect tone for the event. Your unwavering dedication to our association is truly commendable. A heartfelt thank you to AVM retired Professor Ajit Tyagi, President of SAMA, for your inspiring opening remarks. Your vision and leadership continue to elevate SAMA. Special thanks to Dr. Devendra Pradhan, retired Additional Director General, Indian Meteorological Department, for your enlightening lecture on radar principles, including scattering and radar parameters. Your expertise greatly enhanced our understanding of this vital subject. We deeply appreciate Dr. T.V. Lakshmi Kumar, Dr. Rohini Bahava, Dr. Swagata Parra, and Dr. Mili Ghosh Nilala for moderating the Q&A session. Your effort ensured a lively and productive discussion. Actually, we got a lot of questions regarding today's lecture. Lastly, I would like to thank you all the participation for their active engagement and contribution. Your presence and enthusiasm make these events truly worthwhile. Once again, thank you for all making this session a great success. We look forward to your continued support and participation in this future. Thank you.
Thank you. Thank you very much. And our next lecture will be on the next Saturday on 15th June by Dr. Kannan from IMD. So,
Abhilash, I'd like to add that we are thankful to you and entire team of ACARR for conducting this exam session very well. Thank you.
Thank you, sir. So we all next Saturday. Thank you very much.
Thank you, Dr. Abhilash. Thank you, sir.